All right, so we've got a short presentation now about navigating the night sky. So if you're interested in observing or amateur astronomy, if you've got a telescope or binoculars at home, or you just want to go outside and look at the constellations and see what you can find, we've got a lot of good tips for you, showing you certain objects that you'll be able to find over the next few months and how to locate them in the night sky.
All right, so before you can navigate the night sky, it's important to know some basic terminology. So if you do read an article or something that's going to help you with how to navigate a certain thing or look for a certain star, you should know how like the basic terminology works. So one of the base things we use is distances and just degree measurements. So it's very hard to put up like a ruler or meter stick to the night sky. You really can't do that. So a good way and a quick way to actually be able to measure distances is using, your hands. So you could use if you just extend your hand out into the sky, and if you, as you can see with the image, if you put up your pinky, that's approximately the width of your finger at that distance would be about 1 degree in width. If you do 3 fingers like this, it's probably going to be about 5 degrees, and so on and so forth. So that's like a quick handy tool you could use if you want to quickly measure how far something is from a certain object, or just to make sure you understand where the positionings are. One terminology that astronomers really love to use is arc minutes and arc seconds. And if you do read up more on amateur astronomy, you might come across those terms. So 1 degree is about 60 arc minutes, and 1 arc minute is 60 arc seconds. So just to put that into context, for a full moon, that is about 31 arc minutes in diameter. The sun would also be somewhere along that, since we see them both at roughly the same size in the sky. So again, just some quick terminology to help you navigate. Another important thing that astronomers use, especially when it comes to telescopes, because you have to position the scope itself, is right ascension and declination. So as you can see with the image, right ascension is the angular distance that extends kind of eastward from the celestial equator. So you can almost think of it as longitude, like the longitudinal lines you would imagine on the Earth's sphere. So if you have the 0 right ascension line, you could hop your way around the Earth depending on where the position of your, say, star is, and measure it with the right ascension. And a declination would just be basically north or south of the celestial equator, and that's practically like the latitude lines. So instead of using those coordinates, we use right ascension and declination when it comes to astronomy observations, especially when it comes to telescopes.
And another important thing to know with astronomy, especially visible astronomy and telescope astronomy, is apparent magnitude or visual magnitude. So that's a way to measure how bright an object appears in the night sky, and it's a good way to tell whether or not a certain star or deep sky object is going to be something that you can see with the naked eye, or whether you would need binoculars or a telescope to see that. So the way apparent magnitude works is a little counterintuitive. The lower the number is, the brighter the object is. So if you look on this picture on the left here, you can see the sun is down around -26 magnitude. So the sun is the brightest thing on this scale. And then all the way out at the other side towards 30, that would be the dimmest thing on this scale. And the other counterintuitive part about magnitude is that it's not a linear scale. So something that's a magnitude 2 isn't, or something that's a magnitude 10 isn't 10 times as bright as something that's magnitude 1. It's actually a log scale, which means that like each whole number you go up, it's by a factor rather than just by a number. I think for the magnitude scale, that factor is like 2.5. I think that's right, but someone can correct me if they know the exact number. So like
Yes, it's more or less 2.5. Sorry
okay.
to interrupt you. Yeah, like
No,
I think
thanks.
a difference of 5 magnitudes is a factor of 100. So if you
Okay.
have a magnitude 1 star, that would be 100 times as bright as a magnitude 6 star.
Yeah, thanks. Yeah, so basically each time you go up by a number, you would multiply by 2.5 to get the relative brightness compared to some star. So then if you look on the right here, you can just kind of see how bright you're going to be able to see different objects. The naked eye limit at a good dark site, so that's somewhere without a lot of light pollution, somewhere like Stony Brook, or really anywhere on Long Island or New York City, you're not going to be able to see down to magnitude 7 with the naked eye just because there's so much light pollution. But in a dark sky site, you could see up to around 6 or 7. With binoculars, you could see a bit past 8, getting towards 9. 3-inch telescope, you could get up to almost 12, and up from there all the way to, it shows the Hubble telescope there, between 25 and 30 magnitudes. So the Hubble telescope can see things that are much, much dimmer than the naked eye or even a small telescope. All right, and then some objects that are of particular interest are planets, right? Those are good objects for binoculars or telescopes because they're pretty large. Even with a relatively small telescope, you can start to see some detail on a planet like Saturn or Jupiter because they're very large. They have a lot of distinct features. So just to sort of show you why different planets are visible at different times of the year and why they're visible at different times of the night, this is from a site called The Planets Today. And basically what it shows you is a map of the solar system at a given date and time. And this is definitely not to scale. The distances are much farther, and the gas giants and the sun are much greater in size than the Earth. But basically what this is showing you is at a certain time in the year, so at a certain point around Earth's orbit, if you pick a point on the Earth and you choose a time at night, so for this one we chose 9:30, you can see where the Earth is relative to the other planets, and you can see where is it 9:30. So if you see that little bright dot there, that would be where it's 9:30 p.m. So then sort of following the tangent line of the Earth, you can see that this red dashed line is what your horizon would be on this date at this time. So you're not really going to see any of the planets because they're all on the other side of the Earth. So then if we go forward to 4 a.m., the Earth rotates, that point comes around. So now those 3 planets, Mars, Jupiter, and Saturn, are going to be low above the horizon. So you're going to be able to see those closer towards the morning in the current night sky. But now as the Earth moves through its orbit, of course, the relative position to the other planets changes. So if we skip forward to around midsummer, July 15th, you can see that now if you look at your horizon at 9:30 p.m., Jupiter and Saturn are going to be just above that horizon. So you would be able to see those in the early night sky. And then if we go to around midnight, those would be high in the night sky now because you're pointed out away from the sun. You're on the night side facing towards those planets. So you'd have a much better view later in the summer and towards midnight.
Okay, so we could, of course, go into different night skies. We could look at the summer sky, we could look at the fall sky, but since we are, here right now and we have an opportunity to maybe if you could go into your backyard and if you just want to look up, you can look at the spring night sky. It's best seen from late March to late June in the Northern Hemisphere. So again, we're in the prime time to watch it. So the most prominent constellations that are going to be in the sky right now are Ursa Major, which has the very popular, famous asterism, the Big Dipper. You have the Bootes constellation, Leo, Virgo, Cancer. So some interesting constellations that have different interesting things in them. I'm sure some other people in the club have more knowledge on this, like exactly what each constellation has. But some special features that you could look out for are the Lyrids meteor shower, which actually peaked 2 days ago, I believe. They're still ongoing, you can still see them. They're probably not going to be as visible or as bright, but again, if you are able to be in a location, or if you're lucky enough to be in a more darker location and you can see it, that's going to be amazing. Just have a look out for it in the Lyra part of the constellation Lyra. It should be in that direction. Another really cool feature in the night sky is going to be the spring diamond. As some may know, there are different features or asterisms that kind of appear for different times of the year. We have like the Southern Cross and stuff like that. So an important thing right now is the spring diamond, which we'll talk about a bit later. And of course, galaxies. This is prime time for galaxies. A lot of them are visible right now. So we'll probably talk a bit more about them later.
So we're talking about the spring sky. And so I thought I'd just cover why what we mean by that and why the night sky is different in different times of the year. So you can see in this diagram that as the Earth moves around the sun, the area in space that you're looking at different times of the year is different. So in May, for instance, at nighttime or at midnight, if you look straight up to the sky, you're going to see Libra. In September, you look straight up to the sky, you're going to see Aquarius. And in January, you're going to see Gemini. And so as you're going around the sun, at nighttime you're going to be looking in different directions, and that's why you see different stars. And as the good astrologers that we are, we define everything based on these horoscope constellations. Yeah, next slide. Did someone else want to talk about this one?
Yeah, sorry. So just sort of going off of that, why you can see different parts of the sky at different times of the year. This is sort of a diagram of the Earth's orbit around the sun and sort of putting that in perspective to the Milky Way. So the sun is a star in the Milky Way. The solar system is moving through the Milky Way. So as the Earth goes around, let me bring up the pointer, as the Earth goes around its orbit, it's actually pretty tilted compared to the galactic plane. So at different times of the year, basically, if you're looking over here towards the summer solstice, we're on this side of the sun, we're closer towards the center of the Milky Way. So that means when you're on the night side of the planet, you're going to be looking towards the center of the Milky Way. Compared to the winter solstice over on this side, when you're on the night side of the planet, you're going to be looking out out from the disk of the Milky Way. So during the summer, that's why you see the dense disk of the Milky Way. If you're in a dark sky site, you can really see that just naked eye. You can see the Milky Way in the sky. And it's great for astrophotography. If you're trying to take pretty pictures, the Milky Way always looks nice in wide angle shots. So the summer is the best time if you want to see that really dense part of the Milky Way.
So I'm going to talk a little bit about Ursa Major, the Big Dipper, just our classic constellation. It's visible pretty much year-round, as it is a circumpolar constellation. So what's a circumpolar constellation? It means that it never sets. So it just kind of goes around as, while most objects in the sky might rise and set, the Big Dipper just kind of looks like it's going around in circles around Polaris, around the celestial North Pole. So I actually wanted to, so because of that, that means that you can see it year-round. Since it's not like no matter where the Earth is, you're always basically looking in the same direction, regardless of the time of year. I also wanted to point out that technically everything is kind of a star or that empty space where the celestial South Pole would be. Things still look like they're rising and setting maybe, but nothing just travels in a straight line across the sky. Everything's always kind of moving in an arc, arcing upwards kind of diagonally or arcing downwards diagonally as it sets. The only time that wouldn't be the case is if you're on the equator. So you can see in this lovely picture in the background, if you look kind of towards the center of that circle where all the stars seem to be traveling, that's of course where the North Star would be, and things travel in that circle. But as you go out and out more, then you see that things, of course, do set and rise, but in a sort of arcing motion. And if you go to the next slide,
Did it not go for you?
nope. Okay, there we go. Thank you. So here you kind of get a slightly different perspective of it. And again, if you look towards the top left, you can imagine that circle that everything is going around. But then across the center, it looks like something's going in kind of a straight line. And then downwards into the ground and to the right, things are kind of going in a circle, but in the opposite direction. And so that kind of shows you the stars that are going seemingly in a straight line. Going below that would really be stars that are in the opposite hemisphere. So unless you're literally at the North Pole, you can actually see some of the stars that are in the southern celestial hemisphere. And they look like they're going around in circles around where the southern star would be if there was one. So that's just to explain a little bit about the motion of objects in the sky and what that looks like. Go to the next slide now. Okay, so Ursa Major again. It's a really big constellation and is visible pretty much year round, at least from New York. It's one of the easiest things to spot, and it's very big, and it's historically been used by navigators to figure out where they are. If you don't have a compass, you can use it to point your way north. So if you look at the 2 stars that are kind of on the edge of the bowl of the Big Dipper, that's going to point you towards Polaris, as you can see in this picture. It's not a perfectly straight line, it's slightly angled, and it kind of points you towards the Ursa Minor constellation, but Polaris is the brightest star of that in that area. So generally it's going to be hard to miss if you kind of follow that direction. And I like this picture because it's kind of a 2-for-1 here. You can see that if you keep going and you see that big W in the sky, which is Cassiopeia, you've gone too far. And you'll want to double back to reach Polaris. But just by looking at the Big Dipper, you can find the North Star, which is great for navigation, knowing where you are. And you can find Cassiopeia, which is good because the more constellations that you're familiar with and spot in the night sky, those are all going to be helpful for finding even more things. So here's another image just to show, I don't know what the kind of like fixed portion to the left is doing, but I wanted to show this just to give you a sense of what that circumpolar motion seems like. So you can see that even as the Big Dipper is going around Polaris, it never quite sets. Meanwhile, other stars that are further off are going to dip below that horizon. And finally, I wanted to point out Andromeda, who was our champion of the constellation clash. So Andromeda can be found through Cassiopeia, which now we know how to find because Big Dipper kind of pointed to Polaris, and then going beyond that, we found Cassiopeia. And then if we go even beyond Cassiopeia, that angle where Shadar is going to point us to Andromeda. And if you're not too sure, if you forget like which of the angles you want to use, then you can also refer to the Pegasus constellation and that great square of Pegasus, and that's going to also help you guide your way to Andromeda. All right.
All right, so going a little back to the spring diamond, an asterism that you can see in the night sky, as you can see, is a really cool kite diamond-ish shape. It's an asterism that consists of 4 stars. So the northernmost star, Cor Caroli, is actually not the brightest, so it may not be the easiest to see depending on your location. But the other 3 stars are very, very prominent, very visible. Arcturus, which is the star in the constellation of Bodes, is one of the brightest stars. It's actually the brightest star in the celestial northern pole, so it's definitely a very visible thing. Spica, which is in Virgo, and Denebola, which is in Leo, again, very prominent stars, and they make up a really cool asterism. And despite the nice shape, another cool aspect of this asterism is the fact that we see the Coma Virgo cluster that's located inside of this small region, actually. If you go to the next, the next slide, a little more over. One more over, Henry. Yeah, so there's a nice patch of the night sky that spans quite a bit, actually, and it's a very galaxy-rich zone, and as we said, spring is a really good time to observe galaxies, so this cluster is, like this gigantic cluster is the Virgo cluster. You also have the Coma cluster in there, the Leo cluster. They kind of make super clusters on like a larger scale, but these clusters contain up to 2,000 galaxies. We don't have a full number yet, just because it's very hard to get a accurate number so far, but again, they do contain a lot of galaxies that are very unique. A couple of other cool things in there. We could probably show to you in Stellarium a bit more, but so if you do end up going outside and are able to see that asterism, try looking for the Virgo cluster, and if you do have a small telescope or a really strong pair of binoculars at hand, you might be able to try to see. The most you probably resolve is a very fuzzy patch of stuff. That's how a lot of astronomy works, but if you can, that'd be a really cool thing to see. But just in case if you need any help with locating any of it, if you go back to the previous slide, Henry, one saying that astronomers love to use is if you go to the northeastern sky and you locate the Big Dipper, now you have to arc down to Arcturus, so you could see like from the back handle of the Big Dipper, you can kind of go down to the constellation of Bootes and find Arcturus. Then you could just spike down to Spica, and that's a cool and quick way of, you know, finding the constellations and just making sure you have the stars pinned down, so you could later on use that to look for the bigger, the Diamond of Virgo, or also known as the Spring Diamond, and use that to maybe look for the Virgo cluster and other things in the night sky.
Ashita, can
Yeah?
you explain what an asterism is for those that might know not know what that is?
Of course. We all hopefully know what a constellation is. It's just a collection of stars that, you know, you see in the night sky, and we kind of recognize them as constellations. We've been thinking of them as constellations for a while. I believe there are 88 properly recognized ones right now.
Yes, that's right.
So an asterism is sort of like that. It is a collection of different stars, but it's not technically a constellation. It's not like a proper associated thing by the IAU or anything. It's just a shape that's very popular in the sky, and you can recognize it. It's a very recognizable thing, and people could use that to observe different things if it's nearby. It's, again, a very prominent feature in the night sky. So the Big Dipper, which we all remember and know very well, is actually an asterism because it's part of the constellation Ursa Major, even though a lot of people who may not know a lot about astronomy may just assume that it's a constellation in and of itself. So an asterism is just a very noticeable collection of stars.
Sorry, just let me unmute myself. Okay. So now that we've talked about what the spring sky looks like, we should probably talk about a few of the objects you can actually see in the spring sky right now and on through the summer. So it's the spring, which means it's galaxy season. So the Virgo cluster is out. It's a large galaxy cluster. It has about 1,300 galaxies in it, including M87, M86, M84, and M49. I have some pictures of galaxies in the next few slides that I'll show you. And yeah. Right. So these are some of the examples of galaxies you can see up in the sky right now. We have M101, the Pinwheel Galaxy, the Whirlpool Galaxy, the Sombrero Galaxy. These don't look amazing. Galaxies don't tend to look amazing in smaller H telescopes, but you can usually make them out. And then if you want to go to the next slide. Yeah. And also, a main thing that's up this time of year is globular clusters. So if you don't know, globular clusters are pretty much really tight and dense collections of lots of stars. For example, some of these globular clusters, like M3 and M13, they're about like 90 light years across, but they have around like 300,000 or like 400,000 stars in them, so it's super dense. And you can usually see these pretty all right. So I have M3, M13, M5. These are all up. You want to go to the next slide. M92 and M22 are also both up. I mean, in a telescope, I'm going to use stellarium in just a little bit and show you what they might look like through a telescope. But if you want to go to the next slide. We also have open clusters that are up nowadays. So open clusters are like globular clusters, now they're collections of stars. But unlike globular clusters, they have a lot less stars in them and they're a lot more spread out. Like the Pleiades, if you've seen that, as an example of an open cluster. So on the left, you have the Beehive cluster, which is, which is, actually, I kind of wanted to talk about the Beehive cluster real quick for a sec, because it was one of the first deep sky objects I saw in my telescope, and I don't know, I just love the Beehive cluster so much. It's a great sight, but you need like a wide field of view for it. Anyway, yeah, so if we can go to the next slide. And some other stuff that's up this time of year is some planetary nebulae. If you don't know what planetary nebulae are, when a star kind of similar to the mass of the sun gets old, it turns into a red giant and expands, but eventually it sheds those outer layers and they just float away. And those outer layers become the planetary nebulae. So we have the Ring Nebula on the left, which actually looks really beautiful. You can actually kind of see the color in a decently sized telescope. And you also have the ghost of Jupiter, which is named that way because apparently it looks like Jupiter through a telescope, but I've never looked at it. Right. So I think this is the last of the slides, but what I was planning on doing was to show you what some of these might look like in the program called Stellarium. So
I'll go ahead and stop screen sharing, so you should be able to do that now. And then while you're getting that set up, one thing I wanted to comment on, a lot of the objects that Perry showed, you might have noticed, had M numbers. So it was like M51, M13, whatever those objects were. What that means is that they're part of the Messier catalog. That's what M stands for, which is basically a group of objects that were all found and cataloged by Charles Messier, I think in the 1700s. And the reason that that's a really great list for amateur astronomers is because back then telescopes weren't very powerful. Glass wasn't made as well. So for all of those objects that are on the Messier list, those M-numbered objects, those are all really good targets if you're looking for something to see with binoculars or a small telescope, because they're all something that were discovered with small telescopes hundreds of years ago. So those are all good targets. You can just, take Stellarium or whatever app you're using and look for some bright Messier objects that are up, and those should be pretty good to look at through a telescope.
Yeah, what's actually a fun trivia fact is the list was actually compiled because the Messier objects are objects that kind of look like comets, I'm pretty sure. And Messier put the list together so people who are comet hunting would look at it and know that, oh, it kind of looks like a comet, but it's not a comet. Which is kind of a neat trivia fact. But anyway, talking about the objects I just mentioned, let me just check out the presentation, see some of the stuff I talked about. So the Virgo cluster. Let's look at that real quick. So it's a real quick before we do that. This is Stellarium. You can see the night sky here. You see some of the some stars named Vega over here, Capella over there. There's a lot of fun options. See Polaris over here. You can turn on a grid showing you where north is. You can show the constellations. You can see the night sky for any part of the world at any time, which is neat. What you can also do is you can search for things. So for example, if we go to the Virgo cluster, don't know why pinwheel is there, but
isn't that cheating?
Yeah, but we don't talk about that. Okay, so actually, I have to zoom in. Let me just grab my mouse. It doesn't. I can't zoom in with my trackpad. It doesn't work very well. USB is on the wrong side. Right. So if we just zoom into this spot over here, this spot over here, you'll see the Virgo cluster, like I showed in the presentation. This is exactly what it is on the night sky. And what's actually a really fun feature is there's an eyepiece feature where in Stellarium you can put in the telescope you're using and the eyepieces you're using, and it'll show you exactly what you'll see through the eyepiece. For example, I have over here some options. This is through a C8 telescope like the ones the club has. I have a few different eyepieces here. This is the widest field eyepiece I have right now. It's 24 millimeters. It has a magnification of 84 times. And this is what the Virgo cluster would look like if you look at it with a C8 telescope with this sort of eyepiece. We can also talk about some of the other galaxies. What else did we talk about? We talked about the Sombrero galaxy. Just pan over to that. This is where it is in the sky. If I can just zoom out for a bit. Right? So this is what it would look like through a C8 with that eyepiece. Pretty small. Use a bigger eyepiece, and this is what it would look like at about 185 times magnification. I'll show you real quick what globular clusters look like. What a globular cluster would look like through an eyepiece in Stellarium. For example, Messier 3, M3. We pan over to that. This is what would look like. This is what it would look like at the same magnification of 185 times. And again, you can see exactly where it is on the sky, right above Arcturus, which makes this program really useful.
I just want to comment, globular clusters are a really great target for small telescopes because even though you can see that you get a pretty good field of view on things like galaxies and nebulae, they're usually pretty dim, and especially through a small telescope, just looking with your eye through the eyepiece, they're usually just sort of going to look like a cloudy gray blob. They're not going to look like those Hubble photos that you see online and in the Stellarium program here. Because those photos are taken basically long exposure. So there's a camera on a telescope, and then that camera will stare at that same object in space for hours at a time, gathering light. And by gathering light for hours, you get that really pretty picture. But just looking with your naked eye, most of them are going to look sort of gray and blobby. But globular clusters, I think, actually look pretty cool because they're relatively bright. You can see a lot more detail. It's just a really pretty image to see all those stars together in those clusters.
Yes, yes, actually really good. Globs and small telescopes. I was actually looking at M3 the other day, this object through my my 5-inch telescope, and you couldn't see all these outer stars, but like this inner core, you could see it pretty well. You could tell it was a globular cluster. It looked really nice. Also, since we were just talking about the difference between galaxies and globular clusters and how it's more difficult to see one than the other. The thing you want to look at, the number you want to look at to see how easy a biggish object like a galaxy or a globular cluster is, how hard it is to see, is the surface brightness, which Stellarium shows you. Over here we see M3 has a surface brightness of 12.21. If we look at the Sombrero galaxy for comparison, it has a surface, the pinwheel, okay. I guess we're doing the pinwheel galaxy. I got my Messier numbers mixed up. It has a surface brightness of 14.82, which is higher, but remember, lower magnitude means it's a lower magnitude means it's brighter. So a higher surface brightness, or rather, the surface brightness is measured in magnitude for arc minutes. So a higher surface brightness means that it's harder to see. Look at the Sombrero galaxy. It's 11.45, which is apparently the same as Messier 3. Interesting. Anyway, going to some other objects. We can look at the open clusters, like for example, the Beehive cluster, which is again right over here in the sky, but at southwest, right to like top left of Sirius and bottom left of Procyon. And this is what it looks like at 185 times, what it would look like through a C8 with an 11mm eyepiece. We can also real quick just look at a planetary nebulae, one of the ones I mentioned, the Ring Nebulae, see what that looks like. So this is what it looks like with a, actually looks kind of, oh yeah, the Ring Nebula is low in the sky right now, which Stellarium is nice enough to tell me. But if we just fast forward the time a bit, so it gets higher in the sky, and this is what it looks, this is where it's going to be at 12:30 tonight. If we look at it again, it looks a lot nicer. And this is what it looks like again through a C8 with 185 times magnification. If you look at the surface brightness, you'd see it's 10.94, which means that it's a lot easier to see than a globular cluster or a galaxy.
Just noticed, Corral in chat said, I heard Clops might be smaller galaxies that were gravitationally attracted to the Milky Way and had their arms ripped off by our gravity so that all remains are their core stars. Does anyone know if this theory was refuted? I actually hadn't heard of that theory. Has anyone in the club heard that and heard anything about it? Yeah. That would be something interesting to research. I'll
I
have
don't
to
know
look
about
into that.
them being like other galaxies with their the arms ripped off. I actually don't know anything about that theory, but I think globular clusters are generally very old compared to like just random collections of stars that you might get in the galaxy. I think most of the stars in a globular cluster are roughly the same age and very old at that. And the distribution of globular clusters is also different from most of the stars in a galaxy. So where in a spiral galaxy like the Milky Way, most of the stars are pretty much flat. You also have like a spherical distribution of dark matter and globular clusters. So all that being considered, I think the question of their origin is still very much an active area of research. So I don't know if the most popular take is that they were other the current VP actually. So, but thank you. But yeah, I don't know if the most common opinion right now is that they were other galaxies with their arms ripped off, or how they formed. I'm not actually sure. I hope that gives you a little bit more about globular clusters. You're welcome.
And just a few more features, I suppose I should outline about Stellarium, which isn't about looking at stuff really closely. Stellarium is just in general a really amazing program for getting acquainted with the night sky. Over here, I just turned on some options to look at the constellation labels and show you what like the lines are. You can throw on the art too, but that's I'm not a big fan of that. But you can see exactly where the constellations are in the sky. You can actually even set the light pollution level where you are. For example, right now I've set it to 2, but if I increase the light pollution level, you can see the stars slowly start to disappear. As you increase the light pollution, which is really useful for being able to see what stars are actually up and what you might be able to see where you are. You can also, I'm pretty sure, see exoplanets, I think. Yeah, I'm not sure how to actually find it, but I know there's options to see exoplanets, or the stars that exoplanets are circling around, rather, in Stellarium. But yeah, except for that, Henry, is there anything else you want to add about Stellarium?
Sure. Yeah, I could screen share for a minute and just go over some of the very basic features for anyone who's never used Stellarium before. Let me just bring my window up here. All right, yeah, so I've got Stellarium open here. Let me just move my Zoom controls. All right, so just for anyone who's never used it before, when you open it, you're going to be presented with this map of the night sky. I think it'll default to the current time and the current date. So there are a couple of different option boxes on here. So just by moving your mouse into either the left side, the lower left side, or the bottom left, these different options come up. On this left panel here, the first one is the location window. So that's important to set because it's going to be different times of day and different positions on the Earth, and that's going to affect where the stars are in the sky. So you want to make sure you're set to wherever your current location is. Mount Stony Brook Observatory, which is the observatory on the ESS building, is actually a location in Stellarium's list, which I think is pretty cool. So just by searching Stony Brook, you can double click on that and set that as your location. I think I already had that set. But you can pick anywhere on Earth. You can just click a random location. If you want to see what it looks like somewhere, you can pick cities, observatories, towns. You can put in the coordinates if you want to pick a very specific spot that doesn't have a name. And then the next one is the date and time window. So this is important if you're planning to go out and do some observing, either later in the night or on a day in the future that the weather forecast is supposed to be clear. You can set the date and time to when you want to go observing. So right now it is set to the current date, but you can change that by month. You can see how the sky moves around, and you can change the time. So let's see, it's 9:41, so that looks like the current time. Next up is the search window. So that's how you find objects by name or by catalog number. You know, you can type in M13 if you want the Hercules cluster. You can just type in Hercules cluster if you know the name of it, but you don't know the catalog number. If you have a specific position, you can put that in the RAN declination, which are those sort of celestial coordinates that we talked about. You can search through different lists if you're just looking to find objects. They've got all kinds of different lists here that you can look through. Let's see, Messier catalog is a good one because those are good objects to look at with the telescope. And then the search window you can also bring up with Control F, just like searching in a web page or a document. Configuration window is just like basic settings for the application. The astronomical calculations window. I don't think I've actually used this before. Do you know what any of these features do, Perry?
Sorry, I was muted. I don't think I've ever been in here, this menu.
Yeah. Yeah, I mostly just use Stellarium for finding where things are going to be in the night sky to look at. So I've never used the astronomical calculations window, but there's plenty of manuals for Stellarium online if you want to do some more advanced astronomical things with it. That's, you know, well supported.
You happen to know how far forward or back in time you can take it?
You can go pretty far.
Wasn't it like 100,000 years last we checked? Or around there?
So let's see if we go like minus. All right, yeah, so it goes up to about 100,000 years into the past and future. And then, okay, something really cool that I remember we figured out in an eBoard meeting, just playing with Stellarium. Let me go back to that date and time window.
Oh, I remember this. This is
Yeah, okay,
yeah,
so
this is
now, so if we go to today, approximately, you know, close enough. So, oh no, that's not the right one. It is the Crab Nebula. So if we look at the Crab Nebula here, it shows that in the night sky. But now if I go to the date and time window and I change the year to, I think it was 1053. Yes. So ancient Chinese astronomers in the year 1053 or 1054, I don't remember the exact year, recorded a supernova in the sky. And they recorded the position precisely enough that we're able to look at that spot today. And what we see there now is the Crab Nebula, which is this image that you're seeing here. So basically that was a star that exploded. It went supernova and it created this nebula of gas and space from that explosion. So before the year 1054, there would have been no Crab Nebula. And in Stellarium, if you go to the year 1053, in the same position, there is no Crab Nebula. I just think that's a really cool detail that they got right in there. You know, so that if you go forward, it stays there. But before 1054, there is no Crab Nebula. All right, yeah, so then going back to some of those basic features here, you can turn on the constellation lines like Perry showed. You can turn on the constellation labels so you can see what their names are. You can turn on the constellation art. And then there are a couple of different grids that you can turn on here. You can turn on the equatorial grid, and you can turn on the azimuthal grid. So let me just set the date back to today because it also takes into account stellar drift. So Polaris was not the North Star thousands of years ago, and you saw that when we were in the year 1054, Polaris wasn't really aligned with that equatorial north. And that's because of the precession of the Earth, which we've talked about in some meetings before. Basically, the Earth is spinning, but it's also sort of wobbling like a top. So through time, the position of north basically the direction that the Earth's axis points in the sky drifts a little bit. So if you go back far enough or far forward enough in time, you can see that that actually changes what star is going to be near that position. So going back to today, you can see that the equatorial grid shows sort of the celestial north. And then if we go to the azimuthal grid, that's sort of relative to your position on the ground. So straight up is sort of the intersection point of the azimuthal grid, because azimuth is directly up from your position on the ground. And then you can turn off the ground if you just want to be able to see the entire night sky. Turn that back on. You can turn off the cardinal points, whether or not you want the directions to show. You can turn on or off the atmosphere. So it'll sort of add haze around the ground. And as you get higher up in the sky, there's less haze because basically the Earth is curved. And when you're looking low on the horizon, you're looking through more atmosphere because you're looking sort of sideways through a lot of atmosphere. But if you're looking straight up, you're just looking out of the atmosphere. So there's not as much between you and the sky. So that's a cool feature that it has. It adds that haze near the horizon. You can turn on or off whether you want to show deep sky objects. That's a good option to have if you are looking for something to see with your telescope. You can turn on and off planet labels. This is a cool feature. Sort of changes the axis of your view depending on what kind of telescope you have between equatorial and azimuthal mount. Most of the time I just leave that turned off so that it's sort of a normal perspective, but if you want to see sort of the telescope's perspective, how it's pointed, then you can turn that on. If you have an object selected, you can center on it. I don't have anything selected right now. Night mode, this is a good one. If you're outside actually observing and you have Stellarium open on your laptop, you really want to keep your night vision intact. Basically, exposure to bright light is going to ruin your night vision. But red light doesn't affect your night vision as much as other wavelengths. So it's cool that they have this night mode on here so that you can have your laptop out with you while you're observing, turn down the brightness, turn on night mode, and then it won't completely ruin your night vision. Full screen mode, I'll just leave that on. Oh, exoplanets, that's a cool one. So that's how we see exoplanets here. So let me find one and zoom in on it. So it actually shows you pretty precisely here. Let me try to click on this star so that I can center on it. So by clicking that, now it stays centered, and it can show you pretty precisely where, you know, an exoplanet is predicted to be in its system at a given time, if we have that kind of data. For a lot of exoplanets, we can't quite track exactly where they are in their system, but it's pretty cool just that it shows you that they're there. It's definitely not something you're going to be able to see with a small ground-based telescope, but it's cool to look at a star and, you know, just know that that star has exoplanets around it that we've detected with bigger space-based telescopes. You can turn on and off meteor showers, so things like the Geminids, the Lyrids. You can see which direction in the sky those are coming from. You can find the constellation that most of them are named after. The Geminids come from the Gemini region in the sky. And you can turn on and off satellites if you want to see where those are. And those are most of the basic features. So then you've got time, you can pause time, you can play time, fast forward time, slow down time. Yeah, so if you want to download Stellarium yourself, it's free software, right?
Yeah, it's free.
Yeah, okay. It's totally free software that you can download. It doesn't take, you know, a super powerful computer to run. You don't need fancy graphics cards and processing power to run this.
You can get it on Windows, Macs, or even Linux.
Yeah. So I would definitely recommend getting it.
Yeah, I'm actually running it on Linux right now. It's working pretty fine.
So can I say something? One of my coworkers graduated from New Paltz, and their astronomy program actually uses Stellarium as in their planetarium of the New Paltz as their like planetarium software. So it's pretty legit.
Yeah, it's a great piece of software, and it's really powerful, and it's also really nice that it's free. And they have an app too, so you can get it on your phone if you want to. That's not the one that I use personally for, like when you want to point your phone and find things in the sky. The one I use is Skyview. I just find that the sort of the motion gyroscope tracking on that works best of all the apps I've tried. But there are tons of free apps out there that do the same thing on your phone. So Stellarium is great on the computer. It works great on the phone too.
Is
And
Stellarium on the phone free?
I don't know.
I think you have to pay for that, but on the computer it's free.
Yeah,
Okay.
the app is paid. I bought it. It was like $3 or something, but it's paid.
Yeah, I must have paid for it then. All right, does anyone have any questions about what Stellarium can do or how to use it?